I don't know how to turn that off, but I can't wait to figure it out. So the chain rule, I mean, if you look at this rule here, it's a little intimidating. All right, but it kind of feeds into what we were talking about yesterday with the concept of higher order derivatives, but only in the sense that when you have a ddx, you're really just talking about finding the derivative of whatever's contained within the ddx. All right, so if I look at this, I'm just going to kind of hone in on this jammy over here. That could be thought of as ddx of f of g of x. All right, hold on, poor quality, close parentheses, and I need a close bracket. All right, ddx of f of g of x. Now, it's a very subtle change in the way I've created the notation here, but it's really amounting to what we were talking about yesterday, where I was saying, if you have y equals some expression, yesterday it was just y equals f of x, representing the first derivative, or representing the function itself, but then applied with the ddx, making the first derivative. Here we're saying y is equal to f of g of x. This is really the same as saying dy over dx. So same as dy over dx, where y is equal to f of g of x. Now, there's a lot going on there, but it basically amounts to this idea that if we can figure out what f of g of x is, then we'll be able to find its derivative pretty easily. All right. So f of g of x, if you remember from last year, the previous year, I mean, that's not always a helpful thing to say, but I mean, it's old school stuff. It's composite functions or composition of functions. So when you plug one function inside the other, all right. So what we're looking for is the derivative of a composite function. All right. The issue is when you do that, sometimes the composite function is very complicated. I mean, you can flip through the pages and see. Sometimes they're not too bad, but sometimes they're a disaster. All right. So we want to be prepared for the disasters and then, be pleasantly surprised when they're not a disaster. All right. But there are also techniques that allow us to find the derivatives of the decomposed functions. All right. So basically saying, if I could find the derivative of the f of x function and then separately find the derivative of the g of x function, then I'll be in pretty good shape. So the way this really boils down is by saying, all right, we're going to let u equal some function g of x. All right. Or really, it's more like g of x is equal to some variable u, kind of like swapping it out for something simpler. In which case we would say y is equal to f of u. All right. So if I wanted to find the derivative of this, I could do that pretty easily. All right. If I wanted to find the derivative of this, it wouldn't be with respect to x because there's no x in the function anymore. It would be with respect to the u, right? So I would have to find dy over du. The derivative of a function, I mean, it takes on different forms, but one form is the dy, dx, dy, du in this case notation. The other form is the prime notation. So if I'm looking on the left, I would use the dy, d whatever notation. On the right, I would use the prime notation because it's written as a function. All right, so this would become f prime of u. All right. So that would be one part of the derivative. Now, we just made a substitution saying, all right, well, let's get rid of the g of x and call it u. You can't just do that. U is some function g of x. So then what I would do separately is take a look at that u equals g of x and find the derivative of that. All right. And so my two variables here instead of being y and x as they normally are u and x, all right? So if it were y and x, I would say dy dx, but it's not y and x, it's u and x. So I'd say du dx, or quality u. But on the right-hand side, if I'm taking the derivative of that function, again, it's function notation, I just pop in a prime. So this is all well and good. It's great. We have derivatives of each part. We have the derivative of y replacing the function g of x with a u. Great. We have a derivative where u is equivalent to that function g of x, also wonderful. But ultimately, I need dy dx, right? So that goes back to what I was talking about up here, where we have some function where y is equal to f of g of x. So that brings us to this relationship where I have dy over du multiplied by du over dx. If you take those two ratios and multiply them, just this ratio, because, you know, it's very easy to get lost in the notation. You see this, I mean, this looks like a different language here. You know, you show this to somebody who's like 4 years younger than you, and they're like, I'll never be able to understand this. All right. So we're working right now to understand it. But I mean, this is like way beyond, right? But the one thing you can look at is two fractions being multiplied and saying, if I take dy divided by du and multiply it by du divided by dx, what's going to happen? The du's would cancel, and I'd be left with dy over dx, which is ultimately what I was looking for. All right. So what that does is it justifies what we're about to do with the function, but that's a lot of theory. So what we end up doing, and there's actually like 2 or 3 topics, I would say, in the remainder of this unit where I'm going to ask you to follow the process until you start to understand why the process works. Now, if you understood every single thing that I just said, I mean, that's great. You're better than I was when I was in your place, right? Because it took me a little while to digest all that. All right. So you rely on the process, how you actually find the derivative, until it all clicks. And it's like, oh, that's why we're doing what we're doing. All right. There's another process called implicit differentiation and also logarithmic differentiation that we're going to cover. All right. But for now, we're going to look at this and we're going to say, all right, in that example, we have a function y equals u to the 3rd power. I'm going to scroll up in a second. And we have u is equal to 2x squared plus 1. And we want to find each of these 3 different things, these 3 different ratios. All right. So the first one is dy over du. Right now, you'll see here, compared to what we did previously, it's now y as a function of u, but u is a particular function rather than written in general form. So it's not f of u, it is n f of u, right? Some function of u, but it's given specifically as u cubed. So when I take the derivative of y with respect to u, I can actually take the derivative of the right-hand side rather than using some notation. All right. Since it's a power relation, I can apply the power rule. All right. Understood coefficient of 1. Sorry, doing a lot of, you probably didn't need that. Doing a lot of monomial stuff in algebra 1 right now, 3 times a day. So I've been saying understood coefficient of 1 like way too much. So multiply the power by the coefficient, reduce the power by 1. All right. So again, power rule only applies for power functions, right? And we don't want to fall into the trap of using the power rule for things like exponential functions. It doesn't apply there, all right? So the base has to be variable with a numerical exponent, all right? For du dx, that's the second equation. All right, let me scroll up now. Oops. Zoom and enhance. Multiply power by coefficient, reduce the power by 1 for this monomial. So 2 times 2 is 4, x to the first power. The 1 goes away because 1's constant. All right, derivative of a constant is equal to 0 because a constant doesn't change, and a derivative measures the rate of change of a function. No change means derivative is equal to 0. All right. So then if I want dy over dx, I would take my dy over du, multiply it by du over dx. Now, and we learned before that the du's would cancel and you'd be left with dy over dx. That's wonderful. But since we know a particular expression that represents dy over du, and that's 3u squared, and we know a particular expression that represents du over dx, that's 4x, we now have this brand new expression to represent the derivative of y with respect to x. Now, if you can write it as a function of one variable, we want to do that. Sorry, I'll move this up over here so a little easier for those in the back to see. All right, we want to write it as a function of one variable if possible. When you move on to higher levels of calculus, you'll see that functions of multiple variables are perfectly fine, but it's preferred to have it as a function of one variable. All right, so just x's or just u's. All right, in this case, I have a relationship between x and u, and that is u is equivalent to 2x squared plus 1. All right, so any u in here can be replaced with the 2x squared plus 1. And so my derivative, dy over dx, would be this, 3 parentheses 2x squared plus 1 squared times 4x. All right. Now there is a big lurking question here. What's the value of this? Well, it's a rate of change of y with respect to x, which is wonderful. But why did we care about that? What we had were two decomposed functions. We had a y function and a u function. All right. So just kind of off on the side, let me show you what that looks like. This is going back to algebra 2. Honestly, I'm not sure which gap it would be. Probably gap 1. All right. But we have y is equal to u to the third, that was given, and u is equal to 2x squared plus 1, also given. But that y is really a function of u, so we could write that as y of u. That u is a function of x, so we could write that as u of x. All right. So what we would get here is the result of replacing the u with the actual function u of x. All right. This is the composite of the two functions. So the composition would be y of u of x would be equal to 2x squared plus 1. And again, that's our algebra 2 component. All right, what that's saying is that we're taking this function and replacing the u in the y function with that value. All right. So now it's really a y of x, or just you could call it y, because it is the variable y in terms of a bunch of other things, but it's still a y. All right. So that's the composition of the two functions. Great. What does that mean? Well, all this work over here was to find the derivative of this composite function. All right. We were looking at them as two separate functions, decomposed functions, finding the derivatives of them separately, multiplying them together later on to figure out what the derivative would be if we had one singular composite function. And we needed to find its derivative. All right. So it's like, okay, that's great if you have them already decomposed. What if they're not decomposed? I'll show you that in a couple of minutes. All right. But let's do another one where we take it from top to bottom. So number 2, and again, in most of the cases, and the whole point behind working with the functions is decomposed composites, as in they used to be composition of functions. They used to be functions that were one plugged inside the other. The purpose of decomposing it is that you would have 2 simpler functions to find the derivative of, right? So instead of having a monstrosity like 2x squared plus 1 to the third, which actually isn't terrible, but instead of having that, you have something that's power rule ready. It's a tongue twister, so I have to really say that slowly. But you have something that's pretty simple to work with, all right? Power rule ready. Maybe it's a simple trig function, maybe it's a simple log function, but it's not a complicated monstrosity. That's the whole idea. I'll show you a complicated monstrosity in a minute, and then I'll show you how it could be much simpler, all right? So looking at number 2, again, I'm looking for the derivative of y with respect to u. So I have y equals 2 plus, I'm going to write it as u to the 1/2 power. And I have my u is equal to x cubed plus 1. All right, so I just rewrote it to make it power rule ready. dy du, the 2 goes away. 2's, I don't want to say it's irrelevant, but it's irrelevant to the derivative because it's constant. Derivative of constant is equal to 0. All right, u to the 1/2 has a derivative of 1/2 u to the negative 1/2. Derivative of u with respect to x would be 3x squared. All right, so then finding dy over dx is really just a matter of finding the product of these 2. Bless you. Bless you. So just multiplying them together, because one of them is the dy over, that's not a y, dy over du. The other one is the du over dx. Multiplying them together again cancels out the du's, giving you a dy over dx. So the only little add-on step would be replacing the u for what it really is, which is the u cubed plus 1. Now, I will preface what I'm about to say with the third example by telling you that there is a shortcut to this. And I will show you that shortcut. Honestly, if I remember. Last year, I completely forgot. And everybody was so comfortable with this technique that nobody reminded me that I said that there was a shortcut. They're like, no, we're good. We don't need it. So let's give it to the end of the week. If Friday comes along and you're ready for a shortcut, let me know. Remind me, please. And I'll go over the shortcut. It's not really much of a shortcut, but it's something. But if you don't bring it up, I'm definitely going to forget. And also, I'll just kind of assume next year when I'm in the same position that you probably, didn't need the shortcut. We'll see. But anyway, what is this? This is the derivative of the function where x cubed plus 1 is substituted in for x. I'm sorry, for u. Come on, that's supposed to be a nice arc. Didn't end up being that. There we go. So this would be y equals 2 plus radical x cubed plus 1. This function is what we ultimately found the derivative of here. Right? And really at no point did we make things overly complicated. All right. But again, we have to be thinking about, all right, well, we were given the 2 separate functions. What if we were given the composite function and we had to separate them, break them up into two separate functions? How would we do that? That's what the next example is for. Yeah.
Is the y there on the composite function, is that the same as like y of u x?
Yep, you got it. All right, so sometimes it's very easy to see how you can decompose two functions or decompose a function into two functions, sometimes even 3 or 4 functions. We'll get to that later in the unit, but sometimes it's not as easy. But if you have an idea of what different parent functions look like, then that goes a long way. All right, so I can make a list of parent functions, but they're your typical like y equals x squared. I mean, I could start writing this down, put it here. So put some parent functions down for you. Here's some parent functions. And really, I mean, if you've heard the term parent functions in the past, but never really thought about it, or is like kind of dismissed it as a, like unnecessary term, you probably got away with it. It didn't really matter so much in the past, but now it's going to matter more and more. But you don't really need to know the name as much as you need to know the concept. A parent function is the simplest form of any type of function. All right. So we could have a linear function. The simplest form would be f of x equals x. All right. Now, the simplest form would be a constant function. But if we're assuming it's a non-constant function, something that's got some oomph to it, then it would be y equals x. All right. You'd have some sort of power function. Maybe you'd have a basic quadratic. All right. Maybe you'd have a cubic. But really, it's any function with a coefficient of 1 raised to the nth power. All right. So basically, a power function just without the coefficient. All right. But that's the basic monomials, polynomials, things like that. But then you start getting into, okay, well, what about exponentials? Well, you have a nice easy one, the one that we really like, e to the x. Right? You could also have a to the x. That's when the base is some number other than e, like 2 to the x power or something like that. Still a parent function. A little bit more complicated, but still manageable. You could have a log function. You could have another type of log function, but it's not, I mean, it's technically a parent function, but we tend to want to make our logs into base e, a natural log, because it's easier to differentiate, but we can kind of get away with any other kind of log. And then every kind of trig function you could possibly imagine, but without all the bells and whistles. So your basic sine function. So really, there should only be 6, all right? At least until you get to higher levels. Cosine, tangent, secant, cosecant, and cotangent. Now, writing these down should not be like, oh, there's another list of things we have to memorize. These are all things you should look at and say, oh, I'm familiar with these functions. Didn't know they were called parent functions, but I'm familiar with them. It's just basically every function that we've ever learned, just minus all the trimmings. So not sine of like 5x squared minus 42, just sine of x. All right. So what we would do if you want to use this chain rule to find the derivative of some kind of function, what you would want to do is decompose it, but you'd have to identify a parent function that exists. Now, I'm looking at number 3 and I'm seeing sine of something other than x. One of the benefits of using parent functions is that they're the kind of functions we should know the derivative of. All right. So derivative of x x squared, x cubed, x to the nth, that's all power rule. E to the x has a derivative of e to the x. A to the x is a to the x times the natural log of a. A little bit more complicated, but still manageable. 1 over x for the natural log, 1 over x divided by, well, really 1 over the natural log of b times 1 over x. That's why we tend to stay away from this one. We tend to convert it over into a natural log first before differentiating it, just because we don't want to have to worry about that rule. But then we talked about this yesterday. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Maybe you're not as familiar with the other ones, but derivative of secant is secant times tangent. Derivative of cosecant is negative cosecant cotangent. And then cotangent is negative cosecant squared. Right? So, the last three are a little iffy, but they're studyable. Bottom line is those are the functions that we could easily, or relatively easily, find the derivative of. So if I look at number 3 and say, all right, I don't like what I see, but if it said just the sign of some function that was in its most basic form that we would call u, instead of sine of x to the 4th plus 5, I would say sine of u. And then separately, let u be equal to x to the 4th plus 5. Now I have my functions decomposed, because if I replace the u with an x to the 4th plus 5, I get back to where I started, so I know I'm in good shape there. And I also know by the chain rule, I can differentiate each part with respect to the relevant variable. Derivative of sine of u is cosine of u. Second part is just basic power rule, right? 4x cubed. Poor quality 3. All right. So then we put it together to find dy over dx, because if we're looking for the first derivative, we're looking for this, the derivative of this original function, which has an independent variable of y and a dependent variable of x, which means that when we're finding the derivative, we're asked to find dy over dx. All right. That's what this set of directions is saying based off of the notation here. All right. So that's telling me that I have to multiply my dy over du, cosine of u, and my du over dx, 4x cubed. Again, dy over du, and du over dx, simplified equal dy over dx. So that's my license to do that. And since I know that u is equivalent to x to the 4th plus 5, I can make that substitution after the fact and say cosine of x to the 4th plus 5 times 4x cubed. And that would be your derivative. I mean, it's kind of scattered, but it's all there. We have that double equality, but ultimately it's the dy over dx that's equal to the cosine x to the 4th plus 5 times 4x cubed. Now, multiplication is commutative, so you could put the cosine first, then the 4x cubed, or you could do it the other way around. That's perfectly fine. There's no need to simplify. There will come a time and a place where you do need to simplify, but you're either going to be explicitly told to, or you're going to find it necessary to do so. Like if I said find the second derivative, you're going to want to clean up whatever expression you get as a result of the first derivative before you go ahead and take the derivative again. It's just common sense. All right. But there's some questions like number 4 that maybe not quite as obvious, but it's just the way you think about things. Like y is equal to, I'd write this as the sine of x as a quantity squared. Look at my parent functions. And at first, it's a matter of gaining experience. Sometimes it's trial and error. hopefully not too much, but you sort of look at it and say, okay, well, what parent function would be the most useful here? Sine of x, if I let my y equal the sine of x, well, I already have y equal the sine of x to some extent, all right? But if I let u equal the sine of x, then I'd have y equals u squared. It's all about choosing a u that would make the decomposition of the two functions as simple as possible. All right. So if I said let y equal the sine of x, honestly, I don't even know what I would call u. You know, I'd have to think about it. Probably some radical. But if I let u equal the sine of x, then y is a nice simple u squared. Very easy to differentiate. So dy over dx, I'm sorry, dy over du would be 2u. And du over dx would be cosine of x. Then you start thinking about streamlining the process. Since you know that you're going to multiply those two ratios together, and you know in that process you're going to swap out the u for what it really is, combine the steps. So since we know the u is sine of x, I could replace it right on the fly here. So 2 sine x multiplied by cosine of x is what the derivative would be here. Now, this is actually kind of a cool problem, because if you reviewed the product rule, and hopefully you have, if not, got to do that definitely before tomorrow. All right, product and quotient rule are coming up along with the chain rule, so it's going to get interesting. But this expression could be thought of as sine of x times the sine of x. So you could actually apply the product rule instead of the chain rule in this instance if you wanted to. Right? Not necessary, but especially in this case because we're learning about the chain rule. But when it comes down to getting questions right on a test or something like that, that you're going to be left to your own devices to decide, all right, well, what method should I use here? Right? It's more about diagnosing what the appropriate approach is. It's not going to be a matter of use the chain rule, use the product rule. It's going to be find the derivative, all right? And so as long as you could do that using appropriate techniques, you're going to be good, all right? But yeah, every one of these problems has something different that kind of comes into the situation. 5 and 6 should be pretty manageable, although number 6 could be a little funky at first glance, right? But if you make a slight adjustment early on, it gets very easy. But number 7 and 8 are definitely sort of beefy, but I'd say you probably have enough time to give number 5 a shot and maybe get started on number 6 if you haven't started. So I'm going to cut the recording here.